Hello, Accelerated Chemistry students. This is Ms. Christopher, and this is your Chapter 21, Section 2 video notes all over half cells and cell potentials. So let's talk about electrical potential. What causes the electrical potential of an electrochemical cell? The electrical potential of a voltaic cell is a measure of the cell's ability to produce an electric current. So electrical potential is usually measured in volts. The potential of an isolated half cell cannot be measured. You cannot measure the electrical potential of a zinc half cell or a copper half cell separately. When these two half cells are connected to a form of a voltaic cell, however, the difference in the potential can be measured. The electrical potential of a cell results from a competition for electrons between the two half cells. The half cell that has the greater tendency to acquire electrons is the one in which reduction occurs. And that should make sense because we talk about reduction and define reduction as when an element will gain electrons. Oxidation is going to occur in the other half cell. The tendency of a given half cell to occur as a reduction is called the reduction potential. The half cell in which reduction occurs has a greater reduction potential than the half cell in which oxidation occurs. The difference between the reduction potentials of the two half cells is called the cell potential. So the cell potential is equal to the reduction potential minus the reduction potential of the oxidation, or the redox cell potential minus the oxidation cell potential. The standard cell potential E0 of the cell is the measured cell potential when an ion concentrations in the half cells are 1 molar and the gases are at a pressure of 101 kPa and the temperature is 25 degrees Celsius. So again, we're going to put E0 down because that is when we have 1 molar solution at standard conditions, 101 kPa and 25 degrees Celsius. So again, that's the redox half minus the oxidation half. The standard hydrogen electrode is used with other electrodes so the reduction potentials of other cells can be measured. The standard reduction potential of the hydrogen electrode has been assigned to a value of 0. So the standard hydrogen electrode consists of a platinum electrode immersed in a solution with a hydrogen ion concentration of 1 molar. The solution's at 24 degrees Celsius. Hydrogen gas has a pressure of 101 kPa and is bubbled around the platinum electrode. The half cell that happens occurs as follows. We have H plus ions gaining electrons to become H2. So the standard reduction potential of H plus is 0. The double arrow, remember, reminds us that this reaction is reversible. When the half cell reaction occurs as the reduction or as an oxidation is determined by the reduction potential of the half cell to which the standard electrode of hydrogen is connected. So to determine the overall reaction for the cell, first identify the half cell in which reduction takes place. Reduction is going to take place at the cathode and oxidation is going to take place at the anode, remember. So a voltmeter gives a reading of a positive 76 volts when the zinc electrode is connected to the negative terminal and the hydrogen electrode is connected to the positive terminal. The zinc is oxidized, which means it's at the anode. Hydrogen ions are reduced, which means that they are at the cathode. You can now write the half reactions and the overall cell reaction. So we have the oxidation of zinc going to zinc 2+. We have the reduction of H plus going to H2. And when we add those together, remember we're going to cancel out our electrons and we end up with zinc solid, 2 H pluses, zinc 2+, and then hydrogen gas. So now we can determine the standard reduction potential of the half cell by using a standard hydrogen electrode in the equation for cell potential. In the zinc hydrogen cell, zinc is oxidized and hydrogen is reduced. So we're going to rewrite that so that we know that hydrogen is our reduction and zinc is going to be our oxidation. So we can determine the cell half potential by knowing that the overall cell potential is a positive 76 volts. And we know that the standard reduction potential of hydrogen is 0. So we can plug into our equation and solve for what Zn2+ should be. So the standard reduction potential for zinc is a negative 0.76 volts. The value is negative because the tendency of zinc ions to be reduced to zinc metal in this cell is less than the tendency of hydrogen ions to be reduced to hydrogen gas. So here is a chart of standard reduction potentials. I will be giving something like this to you on quizzes and tests in the future so that you can have it as a reference. In an electrochemical cell, the half-cell reaction having the more positive reduction potential occurs as a reduction in the cell. You can use the known standard reduction potentials for the half cells to predict the half cell in which reduction and oxidation will occur and define the E0 cell value without having to assemble the cell. So if the cell potential for a given redox reaction is positive, then the reaction is spontaneous as written. If the cell potential is negative, the reaction is non-spontaneous. So remember, spontaneous means it happens on its own. Non-spontaneous means that it does not. Let's look at an example problem. We're going to run through 3 example problems so that we can understand what we're doing. So determine reaction spontaneity. So show that the following reaction between zinc and silver is spontaneous. So here's our reaction. So what we're going to do is we're going to use the standard reduction potentials to determine if E cell is positive. If it is positive, then it is going to be spontaneous. So what do we know? We know our full reaction, and we don't know if the reaction is spontaneous. So we're going to use that chart to identify that half reactions that we're talking about. Our oxidation reaction is going to be zinc 2 plus going, or zinc going to zinc 2 plus, and silver going to silver solid. We're going to write the both of the standard reduction potentials as we see them on the chart. So our standard reduction potential for zinc is negative 0.76. Our standard reduction potential for silver is a positive 0.8. So when we write that in the correct order and we solve for our answer, we should have our reduction minus our oxidation. So we're going to have 0.8 minus a negative 0.76. So that is a positive 1.56. And since this E cell is greater than 0, the reaction is going to occur on its own and is spontaneous. So zinc is above silver in the activity series, so that means that it will react. And this makes sense that zinc is oxidized in the presence of silver because it has a less less negative standard reduction potential, which means that it would probably be more oxidized. So let's talk about simple problem 21.2, where we're going to write the cell reaction. So we're going to determine the cell reaction for the voltaic cell composed of the following half cells. So we have iron and nickel. Notice how they're both written as reductions because that's how we're going to get it off that chart. They're both written as reductions. And then what we got to do is we have to identify the cell with the more positive reduction, and that's going to be the one that happens at the cathode. So that's going to be the reduction reaction. And then the other one's going to be oxidized. And then we're going to add the half reactions together to make certain that the number of electrons lost is equal to the number of electrons gained. So here we go. We're going to identify the cathode and the anode. So the Fe3 plus half cell is more positive, so it is going to be the one that is reduced. The nickel is more negative, so it's going to be the one that's oxidized. And so we have to write them in that order. So we're going to write these reactions as so. So our oxidation reaction is going to be nickel going to Ni2 plus and then 2E minus. And this is what we have for iron, Fe3 plus an electron is going to go to Fe2 plus. Now what we have to do is we have to multiply the half reaction so we can get our electrons to cancel. So when we do that, this is what we get. We're going to have to multiply the Fe3 plus equation by 2. And then what we're going to do is we're going to add those two together. So when we add those two together, remember our electrons are going to cancel, and we're going to end up with nickel solid plus 2 Fe3 pluses gives nickel 2 plus 2 Fe2 pluses. And remember, electrons are going to be lost by the species that is oxidized, and they must be equal to the electrons gained by the species that is reduced. So if you did that correctly and your electrons cancel, you should get the right answer. Now let's look at our last example problem for this section. So we're going to calculate the standard reduction potential for the voltaic cells that we described in the problem before. So that's going to be the nickel and the iron cell. Here are our standard reduction potentials off of our chart that you're going to be given.
And then the first thing that we're going to do is we're going to use that equation to calculate our standard cell potentials. So we need to look those up off the chart, which is Fe3 plus is a positive 0.77 volts. Nickel 2 plus is a negative 0.25 volts. We know what the anode is, we know what the cathode is because we're comparing, remember, our values. More positive E cells are going to be reduced, more negative ones are going to be oxidized. And then what we don't know is what the overall E cell is. So what we're going to do is we are going to plug them into the equation. So remember, it's reduction minus oxidation. And we're going to substitute our values in, and we're going to solve for a positive 1.02. So the reduction potential of the reduction is positive, and the reduction potential of the oxidation is negative. Therefore, the E cell must be positive. And that is it. That is your notes for Chapter 21, Section 2. And as always, all the information on these Google Slides has been acquired and adapted from Pearson Chemistry's 2012 edition textbook resources CD and pearsonchem.com. Thank you so much. Have a good night.